Hi, I'm Nick Penwarden, VP of Engineering at Epic Games, and I'd like to talk about using Unreal Engine to develop next-generation games. I'm going to start by talking about our priorities and what we're focusing on, discuss what features and next-gen hardware support are in 425, go over our release plans for the year, and then turn it over to Marcus Wassmer, Engineering Director for Graphics, to talk in more detail about some of the upcoming features we're working on and Unreal Engine 5. After that, Jerome Plateau, Art Director for Special Projects, is going to talk about how we built the Unreal Engine 5 demo we recently showed and what it's like for artists and designers to work with the new tools and tech coming in UE5. So I want to start with our priorities and what we think developers will need to ship next-generation games. First and foremost is first-class support for next-generation hardware so that games can take full advantage of the increased CPU and GPU performance, new hardware features, and most importantly, the vastly improved I/O capabilities, which has been a major focus for us. We think developers are going to be building larger, more detailed worlds that will require even more sophisticated content streaming. Unreal already supports streaming levels, textures, and meshes. We're working to optimize those systems, but also investing in systems like virtual texturing and Nanite that can stream in, on demand, only the data absolutely needed to render a particular view, as well as improving tools for authoring large worlds. We think game worlds will be more dynamic and interactive, so we're investing in our chaos physics system to support rich simulation of destruction, cloth, hair, and rigid body interactions, as well as tools to empower artists and designers to create rich, interactive content without needing to get engineers involved. Blueprint scripting, the node-based material editor, and our node-based VFX tool Niagara, for example. As games grow ever larger, more detailed, and more complex, developer efficiency becomes increasingly important. And so reducing iteration times is a major focus for the engine team. Optimizing cooking times, how long it takes to import large assets, and reducing the time it takes to launch the editor. But also rethinking cooking itself and how the engine processes and manages large assets. Online multiplayer is another key component for many games. Unreal has a proven client-server architecture at the heart of our gameplay framework. Our efforts here include reducing the cost of replication to allow games to scale to even larger maps with more players and dynamic objects, and making it easy to write robust, game-specific client-side network prediction code. Especially early in the console generation, many developers will want to ship on both current and next-gen consoles, making it important to be able to scale performance and quality across platforms. We aim to allow developers to build their content once and deploy it to all platforms, and so we build all of our features with scalability in mind. Unreal's rendering features, including lighting and post-processing, support many tweakable options to strike a balance between quality and performance. Dynamic resolution is a really useful tool to maintain a steady frame rate as the GPU cost fluctuates between combat and non-combat or across different views, and also helps you keep rendering features enabled across hardware with different performance characteristics, allowing the faster hardware to scale up quality by rendering at a higher resolution. The Significance Manager offers a framework for prioritizing level of detail or features specific to your games. For example, Fortnite uses this system to prioritize which level of detail to use for characters. And Unreal's device profile system makes it easy to tweak all of these options per device at as granular of a level as you need. And finally, developers need profiling, debugging, and diagnostics tools to ship stable games at frame rate. And for that, we have the size map and reference viewer for understanding what content is going into your shipping game, the low-level memory tracker, or LLM, to understand how much memory is being allocated to different systems and assets, and going forward, we are building up our Unreal Insights suite of tools for everything from profiling CPU performance and load times to debugging animation blueprints. Now let's look at what's in 425. So 425 is the first full engine release to include first-class support for PlayStation 5 and Xbox Series X. That means Unreal developers with access to next-gen console hardware will be able to build, deploy, and run their games out of the box in 425 and make use of Unreal's breadth of features. One of our biggest efforts has been around loading and streaming to take advantage of new I/O hardware in next-gen consoles. Our goal is to vastly reduce loading times so that players can get into games more quickly, and to streaming content more quickly, allowing for richer, more dense environments. To achieve that, we've rewritten and optimized the core I/O and loading systems in the engine in order to minimize CPU time related to loading content. The engine can now identify and load dependencies in an optimal order with significantly less CPU work. We have a new version of property serialization that reduces the cost of deserializing properties by 2 to 6x. And even better is to remove CPU work altogether. We've added systems that help to load memory images that can be used directly without modification. We're using this system to load shader maps for materials. Loading shader maps used to take a substantial amount of CPU time, and now that is reduced to practically nothing. Once components have been loaded and deserialized, they need to be registered with various engine systems. Primitive components register with the renderer so that they can be drawn, and components with collision register with the physics system. We've been optimizing and parallelizing those stages to further reduce the time it takes to stream in levels. That has all added up to about 3x faster load times with Fortnite content, and these changes are available as experimental in 4.25. We're focused on robustness to get these changes ready for production, and also expect to see further gains throughout the year. 4.25 also includes the latest enhancements to our landscape terrain system with non-destructive editing, the ability to create custom brushes with Blueprint, runtime virtual texturing, and updates to the physically based sky and atmosphere model. In 4.25, Niagara is now production ready, having been battle tested in production on Fortnite. For example, all of the water effects in Chapter 2 were built using Niagara. That work has resulted in performance and stability improvements across all platforms and a considerable amount of UX and UI polish, like the scratch pad to quickly author custom behaviors and the ability to quickly specify per platform scalability settings on an effect. Earlier this year, we shipped Fortnite on the Chaos Physics system, utilizing it for scene queries and cloth and rigid body simulation. This work resulted in substantial improvements to performance, memory, and stability in Chaos. Much of that work is in 4.25, with further improvements on the way for 4.26. I mentioned Insights earlier. Unreal Insights consists of two components. First, a tracing API that allows us to collect large amounts of data from a running Unreal process with very little CPU overhead. And second, a visualization tool to efficiently analyze that data. Insights can be used to analyze CPU performance, showing you how long tasks take and which thread they execute on. It can show you what content is being loaded, how much data is loaded from disk, and how much CPU time is spent processing that data. And in 4.25, we've added networking insights, allowing you to inspect packets that are sent between client and server and dig into what data is being sent, which actors are replicating, and so on, to help optimize bandwidth usage. Also in 4.25 is an exciting new use of insights that we're calling Animation Insights. It collects data from the animation system that allows you to see which animations are playing with their blend weights, when notifies trigger, and much more. You can then scrub back and forth in the timeline to see the animation play in an editor viewport. This allows you to quickly debug what's going on when an animation you're working on doesn't look quite right. So that's 4.25, which is out now and ready for next-gen console development. Throughout the year, we will be maintaining a branch of 4.25, which we are calling 4.25 Plus, for developers shipping early on next-gen platforms. We're planning to include bug fixes, changes needed to meet certification requirements, and optimizations with a focus on stability, performance, and minimizing API changes so that updates will be safe and easy to integrate. This fall, we will be releasing 4.26. 4.26 will include new major features like any other release of Unreal, all of the improvements that went into 4.25 Plus, as well as larger optimizations and engine changes for next-gen hardware. Shipping a game on next-generation consoles is the ultimate proof that Unreal is ready for next-gen. We plan to ship Fortnite on PlayStation 5 and Xbox Series X as soon as they launch, so you can rest assured that the engine will be ready. We integrate the latest engine code to Fortnite roughly every season, and any engine changes we make in Fortnite are immediately reflected in the engine main branch for developers to access. So as we make improvements to get Fortnite ready to ship on next-generation consoles, those changes will also be immediately available to developers. So that's 425 and 426. What's next for Unreal Engine? Unreal Engine 5 is coming in 2021 and is going to be truly revolutionary. UE5 will provide a generational leap in fidelity for realistic and immersive worlds and characters, fast iteration for artists, designers, and programmers, and tools that empower teams of all sizes to build bigger games with content that scales. To talk in more detail about what we're working on for UE5, I'm going to hand it off now to Marcus.
Hi everyone, my name is Marcus Wasmer, and I'm the Engineering Director for Graphics on Unreal Engine. I'm here to talk to you today about some technology that we've been building for both UE4 and for UE5. I'm really excited to finally be able to show off some of the hard work that the engine teams have been doing over the last year. So let's just go ahead and jump right in. So one of the primary guiding principles for UE5 is to enable the creation of massive, realistic worlds. We believe that a large living world enables truly compelling gameplay experiences. Players can have huge areas to explore, permanent and interesting agency in the environment, and especially the sharing of those experiences with players in networked play. However, creating a believable world is a real challenge, and expectations only grow with a new generation of consoles and engine technology. If we start with the goal of creating a believable world, a lot of the expected technology naturally follows. A realistic world requires next-generation visuals, believable characters, immersive audio, and much more. So let's start with visuals. When talking about a generational shift in consoles, one of the first things that comes to mind is the potential for more realistic graphics. For UE5, we really wanted to set a new bar for detail, both at the small and large scales. Detail is key to a realistic world, as you really want fine detail combined with a dense and rich environment. Our solution to this problem is called Nanite. Nanite is a next-generation geometry engine that empowers artists to deliver their vision in a way not possible before in a game engine. Nanite allows direct import of cinematic quality assets that have micro-polygon level detail. This means that you can now target assets that can have even one triangle per pixel. In addition, Nanite supports very large object counts with automatic streaming to keep everything in budget. Let's take a look at an example asset. This statue was modeled in ZBrush and comes in at around 33 million triangles. This is then directly imported into the engine with no authored LEDs, and the full source data is available at runtime for rendering. You can get so much detail this way that normal maps are almost unnecessary. On this statue, they are only used for ultra-fine details like scratches on the shield. All the rest of the detail in the shield and armor, even the cut-in grid lines on the chest, are modeled geometry. Of course, many renderers could import this asset and render them slowly, but the true power of Nanite is in scale. This statue was placed around 500 times in this scene. That's over 16 billion source triangles before we even count the architecture, which is modeled at a similar detail level. All of this is running at frame rate on next-gen console. Now let's talk about object density. Nanite not only allows incredible fine detail, but allows an object count to truly fill a believable world. This is kind of a fun visualization that we have for Nanite, where on the left you can see the individual triangles in different colors, so you can really appreciate the polygonal detail. And on the right, we have individual objects colorized, so you can see the placement density of these finely detailed assets. In the city that we're flying through, there are about 500,000 objects streamed in at once, and we can handle a million easily. Let's talk about performance for a bit. We use dynamic resolution and temporal upsampling to 4K for this demo. The average frame hovers at around 1400p before upsample, and the entire Nanite cost from rasterization to gbuffer output was about 4.5 milliseconds on GPU. On PS5 today, GPU time is well within budget for a 60Hz game. Nanite rendering is largely driven by the GPU, so CPU cost is quite small, and does not scale with the number of objects in the scene. So while this demo was run at 30 Hz, these Nanite times are less than the comparable passes we had in Paragon, which was a 60 Hz game, and about equal to the comparable passes on Fortnite, which also runs at 60 Hz on PS4 and Xbox. How about memory though? Imagine if you needed in RAM as many vertices and triangles as all the normal map pixels you have in RAM. How much data would that be if it was stored how we typically store and load meshes? Even though we're streaming only what is needed, the amount of mesh data immediately visible is still massive compared to what we're used to. To keep this under control, Nanite streams mesh data based on the view and keeps it in RAM in a compressed format. The Nanite streaming pool for this demo is currently 768 megabytes, and we expect to reduce that further with improved compression techniques. In addition, compression for disk can be much more aggressive than the runtime compression, and we're working on algorithms to minimize the disk footprint of Nanite meshes. The numbers here are, of course, preliminary, as we have a lot of good ideas how to optimize this. But a good rule of thumb that we gave the art team is 1 million triangles with a single UV channel is roughly the same size as a 4K normal map. Now let's look at Nanite's feature set. We focused fully on opaque, rigid geometry first because this is typically over 90% of the geometry in a scene. With Nanite, you get a true next-generational leap in capabilities for rigid meshes. Billions of source triangles, rendering millions of visible triangles, with hundreds of thousands of object instances, all running on actual next-gen hardware. And to be clear, objects don't have to be completely static. Object movement is fully supported. In fact, the collapsing buildings near the end of the demo are built with Nanite. However, there are some things that we don't currently support. Translucent and masked materials, non-rigid deformation like skeletal animation or world position offset, and tessellation and displacement to amplify source geometry. We will be investigating ways to support these in the future, though. Also, as a quick note, Nanite rendering doesn't lend itself well to aggregates, or many tiny things that become a porous volume in the distance. Some examples are like grass, leaves, and hair. For now, these other geometry types can still be rendered at high quality with traditional Unreal Engine techniques. You can freely mix Nanite and non-Nanite objects in the scene. So I think that covers our improvements in geometric detail. Let's move on to lighting. Realistic worlds are dynamic. The sun moves across the sky, local lights move and change brightness, objects move and are destroyed. We need a lighting solution that is just as dynamic as we want our world to be. So I'd like to introduce you to Lumen, our next generation, fully dynamic global illumination lighting system. In Lumen, all lights and objects are allowed to be fully dynamic. Updates to GI are instant, and with feedback even provide infinite bounces. Even better, this requires no baking and no light map UVs. This is especially important because not only is Realistic World dynamic, but it is large, which makes any kind of baking step impractical for good artistic iteration. So just saying dynamic GI is a bit vague, so let's look at the specific features included in Lumen. Lumen solves diffuse inner reflection, including color bleeding and indirect shadows. With Lumen, you also get infinite diffuse bounces, so you don't have to worry about a single strong directional light, leaving the backsides of your objects unlit. This is also very important for materials with high reflectivity. You also get correct shadowing from skylights, and another crucial lighting feature, indirect specular reflections. These reflections show multi-bounce diffuse and are great for rougher objects. The takeaway here is that Lumen supports the types of dynamic light and geometry changes that are important for games. Time of day, weather, local lights like flashlights, dynamic destruction, and even player construction in the world. Lumen unlocks great dynamic lighting for a new generation of dynamic game worlds. Lumen is an early ambitious technology and is currently running at a 30Hz budget on next-gen console. The team is hard at work optimizing, and we're aiming for a 60Hz budget on release. Also, while Lumen is great on rougher reflective objects, we currently don't support mirror reflections on smooth objects. We're also still working on detail tracing to reduce light leaking and achieve better results in architectural settings. Lastly, we're investigating more options for scaling, so you can choose where you want to make your trade-off between quality and performance for your project. In summary, Lumen is working today on next-gen console, has a great feature set, and gives amazing results for runtime dynamic lighting, as you can see here and in other examples in the demo. All in all, we're incredibly excited to see what UE5 content creators can achieve with the power unlocked by Nanite and Lumen working in tandem. Okay, so now you're thinking, geez, this tech could be great, but how am I going to create all these realistic assets? Well, one thing that should definitely help is Quixel Megascans. Quixel joined the Epic family last year, and we worked quickly to release the Megascan library for free for all Unreal Engine users. There are thousands of photorealistic assets that span environments from all over the globe. These are available both on the Unreal Marketplace and through Quixel Bridge. I really encourage you to check these out if you haven't already done so. In fact, our own demo content was built with Megascans. And I'm happy to announce that even more scan types are coming soon. Quixel will be releasing new, large-scale scans like cliffs, terrain, and mountains, as well as modular scans for buildings, streets, pipes, and even trees. The Megascan set used for this demo will be available as well. Now, more than just lighting and rigid geometry, you often really need some visual effects to make things come alive. To help with that, we've added even more great features to Niagara. The first thing you'll notice in 425 is a new polished UI that's much easier to use. We've also done a large number of stability and performance improvements for both CPU and GPU. In addition, we have brand new features like an audio waveform data interface that allows your Niagara systems to react dynamically to playing audio. Also, a suite of new features which allow particle-to-particle communication, which allow Niagara users to build complex fluid simulations, flocking behaviors, and much more directly in Niagara. You can see these on display in the demo in the water, wildlife, and portal effects. To get started with Niagara, I highly recommend watching the Inside Unreal video with Wyeth Johnson, giving an in-depth look at the release, as well as a great tutorial video by Chris Murphy on how to create a complex character effect that would have been impossible in Cascade. Of course, let's not forget characters. Humans are a critical component of many games, and character rendering is rapidly advancing. UE is at the forefront of real-time digital humans, and you can see some examples along the bottom here. Senua in the new Hellblade 2 trailer from our friends at Ninja Theory is a great example that you should check out if you haven't seen it yet. Probably the most important recent improvement to character rendering in the engine is our new advanced strand-based hair system. Fully integrated with physics, the hair sim and rendering combine to give a great result. This was first available in 4.24 as experimental, but has had a number of improvements made for 4.25 with more to come. The next improvement for character rendering will be a fully customizable mesh deformation system for UE5. Currently, UE4 supports a more hard-coded path of standard GPU skinning, morph targets, and tangent recalculation. However, UE5 will have a framework where you can create your own custom deformation rules and order them according to the desired result. This should open the path to a lot more creative freedom and realism when it comes to facial animation and body motion. Of course, rendering quality isn't the only aspect of making a believable character. You also need high-quality, realistic animation. For this, the animation team has been hard at work at a suite of features. First is Control Rig. This is a scriptable system that lets tech artists create complex, high-level controls on top of an animation skeleton, as well as enabling per-bone procedural control. Control Rig is currently available in experimental form and is planned to be fully production-ready in UE5. Also today, Rigid Body and Cloth Sim are fully supported with the new Chaos Physics system, and we have a new animation debugging tool built into Unreal Insights coming up in 4.25. If we look to the future though, we've got some really cool stuff coming up. First is a full-body IK solver that will be shipping in 4.26. It's important to note that this is just the solver, but we'll be building a set of tools and APIs around it for UE5 to integrate more fully into the pipeline. Also in UE5 will be a system for locomotion warping. The idea here is that we want to provide a way to get high-quality, believable animation, but with sparse data and fast iteration. For example, if you record a walk cycle on a flat surface, and you want to reuse it on an arbitrary slope, you'll be able to do just that with slope warping and not need to record separate animations for that case. Stride warping is another example where a walk cycle could be extended into a jog or run automatically. You can see some usage of these techniques in the demo video. I should call out that these systems are intended for more than just bipeds as well. Now, I mentioned the Chaos Physics system before, so let's talk about it real quick. Going back to our goal for UE5, we notice that a realistic world is also an interactive one. Many games worlds are largely static and non-interactive. We wanted to help move the needle on that, and so build a new physics engine from scratch. Chaos is custom-built, tightly integrated with the rest of the engine. It's a full PhysX replacement, and in fact, PhysX will be deprecated in 5.0. It was designed for performance and for rich feature set, including massive scale destruction. I definitely recommend checking out last year's Chaos demo for a look. It has also now been shipped on Fortnite on all platforms, so it's definitely been battle tested. The big upcoming thing for Chaos in UE5 though is going to be large-scale networked physics. We want players to be able to interact with each other and the world together, and we're going to power that through Chaos. And now, last but not least, let's talk about audio. Amazing audio really helps to sell a believable world, and the auto team has been working hard to make this easier to achieve than ever. The foundation of audio in Unreal Engine is now called Audio Mixer. Audio Mixer provides consistent multi-platform rendering for all sound sources. Previously, it was extremely difficult to author audio that was consistent across platforms due to differences in feature sets across platform APIs. However, Audio Mixer provides high-quality, high-performance, consistent rendering of audio effects everywhere. This is now the default in 4.24 and has been shipped in Fortnite on all platforms. The next two features are also pretty exciting. First is convolution reverb. This is a process for simulating the reverb of a space based on real-world samples. This means that you can take a recording of a real location and apply its properties to any sound source, making it sound as if you were really in the recorded location. This is a big improvement over traditionally simulated reverb effects. Also, we've added sound field ambisonics. If you're familiar with graphics, these are similar to spherical harmonics techniques. Basically, you can play back sound field recordings as audio skyboxes, which can be properly rotated according to the player and environment orientation, and these can even be recorded in real environments with special microphones. They really improve the spatial depth and realism of ambient audio. Both of these features are available in 425. Okay, so we've talked about a lot of really awesome features, but let's talk about development for a bit. To create a massive realistic world, you've definitely got to have tools that scale with the content you need to build and make it easy to create a lot of content quickly. That's why we're also spending a lot of time on the editing experience for these worlds. First up is a suite of open world systems built directly into the editor in 426. We'll have water, roads, and a new volumetric cloud system available later this year. In fact, the volumetric clouds are currently in dev rendering on GitHub in an early state if you want to take a sneak peek. The water system will be essentially the same system used in Fortnite Chapter 2, but polished up and integrated directly into the main editor. For UE5, we wanted to tackle some other problems. For example, we'll be adding an automatic grid-based editing and streaming management system. This will supersede the world composition system and provide automatic streaming of objects based on their location in the grid. Grid cells will also have hierarchical LOD and imposter generated for them, saving a ton of work and setup of these optimizations. Also, we want to make it easier for large teams to collaborate in a large world. That's why we're moving to a file per actor system. With a file per actor, you no longer have to worry about one team member having exclusive checkout to a grid cell or sublevel, and everyone can work together on sections of the world at once. Lastly, we're adding a system that we call foundations. Foundations are effectively instanceable sublevels that can contain other foundations. This will allow you to create a hierarchy of pieces that you can reuse to populate your world. For example, a foundation of a floor or a building could be combined with multiple floors to create multiple building foundations, which can then in turn be used to create whole city foundations. Foundations will also get their own hierarchical LODs automatically generated and have streaming automatically managed. So I touched on this in a previous slide, but developer efficiency is more important than ever. Next-gen games are likely to be bigger and more complicated with higher expectations than ever before. That's why we're making a dedicated effort on the engine team for fast iteration times in UE5. The faster you can iterate on things, the faster you can make them great. Like I said, this is a huge cross-team effort across all of our engine teams. We're focusing on things like improved cook times and infrastructure. In fact, we've already made improvements in 425 that show cooking for Fortnite with a hot DDC is 2 times faster than previous releases. For UE5 though, our goal is for you to run on a console or phone nearly as fast as Pi. We're also working to improve automatic SDK and firmware installation, signing, and deployment. The overall guiding principle here is that we want to be able to give a new device to any member of a team and have them up and running in a coffee break. Another growing problem in the industry is just the sheer size of projects. Right now, a full sync of a Fortnite stream is over 300 gigabytes. This can be a real pain when you're working remotely, and even just managing hard drive space when there's a few active streams you need to work in can suddenly become a problem. To address this in UE5, we're working to implement an asset virtualization system. Asset virtualization is basically the idea that instead of pulling down an entire project's worth of data, you instead pull down a small set of metadata about the assets in the project. The real full data should then be stored on some fast shared storage, of which there will be multiple possible options here. Then the full data is only downloaded locally on demand by the editor. This means that you only have to pay for the time and drive space for things that you actually use. So if you only need to hop into a single level or zone, you can be up and running much faster than if you had to pull down an entire project's worth of assets. This will be a huge value to all teams with a significant amount of content. Okay, so we've covered a lot of exciting tech here. So let's talk about the transition from UE4 to UE5 a little bit. First off, I want to note that just because we're talking about next-gen, current-gen consoles are still very important. Many titles are going to be cross-gen, and mobile is still a great platform. UE5 will continue to support all of these. In addition, UE4 is already built for a unified content pipeline, meaning you can build one game and one set of assets and deploy it with a wide range of scalability from high-end PC all the way down to mobile. UE5 features are built with the same mindset that you should get representative content on all platforms with a single set of source data. But let's take a look at the timeline again. It's important to note here that the UE4 to UE5 transition is not a hard break. Your UE4 projects will continue to work in UE5. You can think of it as a larger than normal UE4 point release upgrade. If you've got engine modifications, it'll be harder, but not 10 times harder. And I want to reiterate that UE4 will fully support next-gen platforms. This means that you can upgrade your existing projects on your own schedule without missing out on the console generation shift. And to make sure that UE5 is ready to go right from the start, we'll be shipping Fortnite on UE5 on all platforms before the final release later in 2021. So we really encourage projects that will be shipping after that time frame to go ahead and move on to UE5 as soon as possible to take full advantage of Nanite, Lumen, and all the other improvements in development efficiencies. Okay everyone, that's it for me. I hope you're all as excited about UE5 as we are. And now I'm going to hand it over to Jerome, who's going to give you an in-depth look at how we actually created our UE5 demo.
Hello, I'm Jerome Plateau, Art Director of the Special Project at Epic Games. In this video, I will show you what it's like to work with the new features like Nanite and Lumen in Unreal Engine 5. So to develop those new features and test them in a real production environment, we put a demo together. You can see the full video of the demo running in 4K on the PlayStation 5 in our Unreal Engine channel. But for better context of this video, let's take a look at our teaser that highlights some of the new technology for Unreal Engine 5.
It might be.
Okay, so let's first of all talk about the asset. With Nanite, we can import assets with large amount of polygons. So we have decided to take advantage of it and incorporate that into our style and visual language. We wanted the demo to have the same amount of polish and refinement everywhere, so the player could explore every corner and enjoy all the details. Let's use that statue for example. The idea was to push the modeling where the small shapes are actually changing the silhouette. That's something that could not be done with just a normal map. Notice how the ornaments are catching the lights and casting shadows. It helps to create a great sense of scale. This statue has 33 million of polygons. The modeling started in 3ds Max and was refined in ZBrush, where we have added all the intricate details. The final version of the ZBrush model was imported straight into the engine. That means no baking of normal map from high resolution asset to the low resolution game asset. Also, we didn't have to author any LODs. Nanite is capable to handle the asset the exact way it was modeled without any loss of quality. So without doing the retopology of the asset, baking normal maps, generating LODs, the artists don't waste any effort on the content creation side, and can spend their time making high-resolution assets. Editing UVs for such a complex model becomes a bigger task. That is something that you need to take into consideration as you are modeling the asset. A lot of our assets are so heavy that it becomes hard to edit them in regular DCC packages. That means we tend to split our asset into more pieces than we are used to in the video game industry. Our workflow is actually getting closer to the visual effect industry now. On the left side you can see our zebra sculpt, and on the right side this is the amount of geometry that will be imported straight into Unreal. Again, here is a close-up of the teeth, where you can see how much detail is being imported in the engine. Here is our painted version of the model in Unreal Engine. The only normal maps that we used are for the tiny scratches and the fine surface detail. Those are easier to edit and iterate in the textures. Unreal Engine supports virtual textures. We can now have texture resolution of 8K without overloading the GPU memory. The statue was separated into 8 pieces: head, torso, shield, etc. Each piece has a set of 3 textures: base color, metal and roughness, normal maps for the surface detail and scratches. That means for this asset alone we have 24 textures of 8K resolution. Here is the final paint of the face. And here is the underlying geometry. This is not noise. Each area of color represents a triangle. And here is the close-up of the teeth in Engine. And as you can tell, all the geometry information from the zebra sculpt was conserved. So this is what we call the graveyard room in the demo. This is where all the statues of the ancient warriors are stored. So we apply the same amount of care and detail everywhere in the environment. All the friezes, the ornaments, the props have the same amount of detail. That room has nearly 500 of that exact statue at the same detail, which represent a total of over 16 billions of triangles for the statues alone. Here is a representation of each of the triangles in different color. Most are so small that they look like noise. Nanite achieves detail down to the pixel, which means triangles are often the size of a pixel. In this view mode, each object is represented with a different color. Nanite can support scenes with more than 1 million of objects. That means we don't have to merge assets together to reduce the amount of draw calls. That also means we don't have to generate hierarchical LODs. Everything in the scene is live and can be adjusted or moved at any time. For the cave section of the demo, we wanted to keep the same approach and have the same amount of detail. So the player could examine it anywhere in the environment and enjoy the same amount of realism. For that we use the fantastic Quixel asset library. Each asset in the Quixel library comes in different versions, from the most optimized version for mobile game all the way to cinematic quality. Of course, for this demo we wanted to push the quality as far as possible, and we used the cinematic asset instead of the game asset. The cinematic assets are made of millions of triangles. In that case, the rock has 1.5 millions of triangles, and we also use the 8K textures. As you can see on the left, a lot of assets are scanned with terrain around them, which is great to integrate with the floor. But we wanted to use some of the assets for the walls of the cave. So, to add extra modularity, we processed the asset in Houdini, where we removed the extra skirt around the asset and did a vertical mirroring. On the right side you can see the mirrored version. We have also added extra noise to hide the seam in the middle. Here is another view of the cave and the corresponding polygon density. Here is another close-up. And again, you can see the same amount of detail here. But Nanite doesn't have to be constrained to small rooms, it can stretch all the way to the horizon.
Don't fail me now.
For the final part of the demo, where the player glides through the Forgotten City, we use the same type of asset. On the left you can see the triangle view, in the center this is the final render, and on the right this is the object view. Notice the consistency of the triangle density on the left, and how far you can see the individual assets in the object view on the right. Over this entire demo, there is hundreds of billions of triangles.
It's time to see what's next.
Manipulating thousands of assets made of millions of polygons and thousands of 8K textures can be challenging and time-consuming. So to deal with that many really heavy assets, we need to have a solid pipeline. For that, we developed our node-based pipeline using Blueprint function library in Python. This graph is obviously a very simple graph. The last node is a Python script that is represented as a blueprint node. In this case, the Python script simply opens Maya. So that means that now I have a blueprint event that is going to open Maya. But your pipeline could be something like that. First, you could initialize your variable like asset name, asset path, shotgun information, etc. Then the blueprint could open Maya, export the geometry into an FBX, then the FBX could be imported into Houdini and being processed, then the final geometry could get imported into Unreal in the correct folder. Then you could update the substance spec and re-import the texture in Unreal and assign the texture to the material and assign the material to the asset. Then you could kick off a render of the turntable, publish the MP4 into Shotgun for review. Once that's all done, you could also send an email at the end of the graph. But because it's all node-based, you can reorganize the pipeline the way you want. Here are some examples. At the top, it's a tiny portion of our geometry importer, and at the bottom, this is our turntable graph. But of course, with the power of Blueprint, you can go as complex as you want with your pipeline. Those graphs were set up by our technical artist and wrapped into a widget with some UI to make it easier for the rest of the artists on the project to utilize the pipeline. On the left, this is an example of one of our widgets, and on the right, this is a Maya scene with our library of statues. In this widget, we can point to a Maya file. The widget would list what assets are in that file, and we could select the ones that we want to import or update. Then we can tell the widget what would be the master material for those assets, and then the tool would instance the master material and assign the new texture into it. And then once it's imported into Unreal, we could just launch a turntable. But you can go as nuts as you want with those widgets. Each button can run a part of your nodal pipeline. Now let's talk about lighting with lumens. Lumen is our new fully dynamic global illumination technology. For an artist, it means that we don't have to bake the scene to see the result of the indirect lighting. Notice how the light bounces between objects that are far apart, and as well on those tiny scattered objects on the ground. Okay, let me show you how it looks like to work with Lumen in Unreal Engine. This footage has been captured in Editor on a regular high-end gaming PC. In this case, I'm simply rotating the spotlight. Notice how the light coming from the spotlight bounces back on the wall and the stalactites. Everything is updated in real time. And when you change the color of the spotlight, you can see the bounce light being updated too. Now I'm changing the intensity of the light. And notice how the GI and the atmosphere are being evaluated in real time. Let's take a look at what happens when you modify the environment. This large chunk of cave is made of several Quixel assets bunched together, which represent millions of polygons. We can move that large amount of polygon and you can notice how the lighting is being updated in real time. But let's see how it looks when you completely obstruct the entrance of the cave. Let's take a look at how we did the side dressing of the environment. Like I showed you earlier in the city, we can now have scene with millions of objects. Let's focus on a small corner of the cave to give you a sense of how many assets are being used. Again, each asset is at least 1 million polygons with 8K textures. and we maintain the same quality of set dressing throughout the demo. Here is another area of our demo. The side of the temple entrance are made of hundreds of pieces, and notice how the lighting updates in real time. One more big improvement is our new sky system. In this case, I'm rotating the directional light. Notice how the shadow and the GI in the valley is getting updated. The sky color also changed based on the position of the sun and the volumetric cloud shading update in real time. We also have control on the density and the shape of the clouds. One more thing that I wanted to share with you is the flock system that was used for the bat and the bugs in our demo. For this effect, we use a static distance field volume texture to place insects on the level's surfaces. Their macro animation comes from a Niagara-powered state machine, which transition between calm, excited, and seeking states. Thank you. And now let's go back to Nick.
Thanks, Jerome, and thanks, Marcus. And thank you for joining us today to hear about our plans for next-generation development in Unreal Engine. 4.25 is ready for next-gen development, and the 5.0 preview will be available early next year. So you can get started now and bring your projects to UE5 when ready. I really can't wait to see the next generation of games that developers create with Unreal.